So welcome everybody to our Friday seminar. We are very pleased to have a guest, Ruoshi Liu, with us in person. So thanks very much for making the journey. Ruoshi came up from New York this morning on an early train. Ruoshi is a third-year PhD student with Carl Vondrick. And I have known Ruoshi now for about a year and a half when I went to go and talk at Columbia at the time. And Ruoshi and I talked about a very interesting project to do with using thermal images which have a different reflection characteristic that lets you do interesting things like try to estimate the human body pose from regular surfaces around the world under reflection, even if you can't see them under visible light. And more recently, he's been working on generative models and had some infamy with this work 0123, which was at ICCV, I think, just a minute ago, and allows you to have variable input images into a generative model and get out some three-dimensional shape and appearance. So that's very exciting too. So with that, I will pass over to Ruoshi and say we're very pleased to have you here. Thank you very much.
Thanks, James, for the kind introduction and like a preview of what this talk is about. Yeah, so as the title suggests, I'm going to talk about generative models and 3D computer vision today. Like generative models are very popular nowadays. So I want to start with like a quick literature review of like what we've done with generative models over the years and how are they looking right now, like where we are, right? Yeah, so in terms of like 2D generative models, I want to start with like a 2006 paper by a now professor at UCSD, Joanne Tu's paper. It's called image parsing. So they use like a PCA model, and then they create like a very early version of like a generative models of faces. And then this is like the results at the time. And then in 2010, and there's the famous deep belief, like they proposed like a architecture called deep belief network, which is the early sort of version of like deep learning. It's at the time like before everyone knows about deep learning, right? And then they thought the results were so impressive in the NeurIPS 2010, they created this video. I think someone is. I see. I don't think I can play the audio. All right, I'll skip this section. Basically, there's a bunch of famous people talking about their deep belief network, just to hype it up so that people pay attention. So it's apparently very hard for people to pay attention to deep learning at the time, basically. And you notice a lot of like familiar faces, like Ruslan from CMU and Dave Fly, and then these are basically big names now, and they're making this funny video. So there's a Twitter link here for the video, so if you're interested, see that. Yeah, and then in 2013, there's the famous VAE paper, or variational autoencoder, and they basically improved upon the previous version of generative models, and they can generate much higher quality faces and with some nice properties, right? And very interestingly, there are actually two parallel papers on that propose the VAE model. There's a famous one coding variational AES by Kingma and Maxwelling. But there's also a DeepMind paper that's submitted just about like 3 weeks after the first VAE paper, and you get like 10 less time citation. So next time you cite VAE, make sure you cite both.
The first one actually is the first one I read, interestingly enough.
Okay.
Before the second.
So interesting.
Yeah.
And then in 2014, there's a famous GAN paper, Ian Goodfellow. And at the beginning, like the results were not that great. Like from the faces here, it's not that different from 2006 paper. But it's the later work that make GAN much better in terms of image quality and generation results. And then in 2015, there's the like normalizing flows. they're very interesting as an architecture. They're very nice properties, like they're invertible, but they never really create results that are pleasing enough to make it to the mainstream sort of generative architecture. So they still remain like a niche in the generative models research. So I would not go into details of that. So in 2017, there's the VQVAE paper. They use vector quantized representation as a bottleneck for image generation. And then they that was the sort of state of the art at the time. These are some unconditional results trained the training of VQVA to generate images. And in 2018, there's the famous Salgan paper by NVIDIA. And then it was sort of the first time you could use GANs to generate photorealistic images that fool human perception. Like you can't tell what's the fake image and what's the real image anymore. So that was a big hit at the year. And then in 2020 and 2021, there's a DD paper that it's not first introduces the diffusion, but it's the first sort of show that diffusion models can beat GAN in image qualities. And they showcase very stunning results. I remember I was very surprised by the results of this paper. And then at the same time, at the same year, or slightly after that, OpenAI released the DALL-E first version of DALL-E, which uses a VQVAE and clip representations, and they could pretty much do zero-shot text-to-image generation. And then, a year later, it's basically the three main work that came out, where probably most of us are familiar with here, is the DALL-E 2 Stable Diffusion Image Gen from Google. Right, all of these papers use diffusion models as some sort of text image multimodal representations for text to image generation, and that was sort of the time that vision generative models have really gained a lot of attention and momentum in research and in the industry, of course. And then in 2023, which is this year, there's the Muse from Google, which uses autoregressive architecture for image generation instead of diffusion, and there's some bent right here that diffusion are better nowadays just because there are more open source diffusion papers, and autoregressive models are still in the game basically. So that's interesting. It's open research questions we're not sure about. And there's also the famous Midjourney V5 that create very stunning photorealistic images. And looking back in this over a decade of progress in vision generative models, we've gone from very rudimentary generation results of faces to very photorealistic Midjourney generations that contains all of these stunning details, right? Reflections, shadows, and a lot of shadings. That's basically I can't tell if this is a real image or if it's generated by Stable Diffusion. And looking back from the 3D side, I guess it's fair to say that it starts from 2016 when Jiajun Wu wrote the paper called Learning Probabilistic Latent Space of Object Shapes via 3D GAN. So they basically train a voxel GAN in 3D to generate voxels, shapes represented by voxels. And then later, in 2018, it was a sort of a year when implicit representations of 3D become very popular. So there's a occupancy net paper, and there's a deep SDF paper. So they basically, you're able to generate watertight meshes or pretty high fidelity 3D shapes with data sets like ShapeNet. In 2019, there's the IAM-NAP paper that improves upon these implicit representation generative models, and it's generating higher quality 3D shapes. In 2020, there's the famous graph paper that you could generate basically texture and geometry at the same time, I think with NeRF as a representation. And in 2021, there's the EG3D paper by Gordon's group in Stanford that basically allow you to generate very high quality images, like 3D rare images. Basically, you could view 3D, some sort of 3D structure from the faces, images like faces. And in 2002, which is last year, there's the famous Dream Fusion paper, right? That basically was a huge hit at the time, that you could generate 3D scenes of nerves from basically a text prompt. And the way it functions, it optimizes for a nerve field with gradients produced by a diffusion models, like a text image diffusion models. And there's also OpenAI also released the Point E paper, which I'm sure some of you here are aware of. So instead of like basically Dream Fusion is not really generative models, right? It doesn't really generate from any distribution. So Point E is by definition more of a generative models. They have a huge 3D assets library that's not publicly released, and they train like the generative models to generate point clouds. And today's talk, I want to basically talk about, like, on the 3D side, how do we go from here, right? Now we have Dream Fusion and Point E, which are pretty impressive, but they're not quite there yet. So I want to talk about what's next. Yeah, so in addition to that, so the first question I want to answer is, how do we build better 3D generative models given the current state of the art? And the second question I'm also very interested in is, assuming that 3D generative models keep getting better and better, which I think most of us will agree, right? There seem to be exponential growth in the progress in generative models. In a few years, right? Like in the future, if we get better and better 3D generative models, how do we use these generative models for computer vision tasks? Which, you know, as computer vision researchers, we probably care a lot about this question. Yeah, so I will talk about some of my work that try to answer these two questions basically in today's talk. So I want to start with the Observerse XL, which is a paper just got accepted to NeurIPS this year, and then we also just released the data set a while ago. So looking back at the timeline of vision generative models, right? It's probably the underlying story there, I feel like, is that the high quality data set is the unseen hero here. So we definitely have better and better generative architectures and different ways to train, better and better ways to train generative models. But the progress is definitely also driven by the progress of better and better data sets, basically a lot more diversity, higher quality, and just bigger in scales, right? So before 2010, we basically have MNIST scales image data set, and when we have ImageNet, we have much better generation quality in the image. And like recently, we have like LION, like open world data set or internet scale data sets, like LION 5 billion. That basically breeds a lot of the recent, like very impressive generative models. So on the 3D side, Observerse XL is a data set with 10 million plus high quality 3D assets. So to put things in scale, this is everything else before Observerse. And then this is Observerse 1.0 and this is Observerse XL, right? And Observerse comes from a diverse sources on the internet. So the majority of the assets are coming from GitHub, just like people uploading their assets to GitHub. And then there's also several websites that we source our data set from. And to break things down a little bit, right? Like as you can see, most of the assets come from GitHub, and actually almost half of them are duplicates, basically. Like people uploaded same assets to different places, so we have to get rid of those. And then there's in the remaining of them, only less than half of them are basically be able to convert it into to be rendered in Blender engine. So we also throw away. So we only keep like less than 1/4 of what we downloaded at the beginning. So there's some room of improvement as well, but not much more basically. Yeah, so this is the Observerse XL data set. It's very exciting. You know, like 10 years ago, ShapeNet was released. It was like maybe less than 100K. Now we scale it up to 10 million, right? And in order to keep scaling sort of 3D assets, another way sort of is to augment the 3D assets, right? So this paper we just submitted to iClear, it's called Syn3DM. It's basically a method for you to do 3D data augmentation from just a single 3D asset. So the way we do that is we train a 3D asset autoencoder first. So we basically use a 3D ConvNet to encode into triplane representations. And then we decode it with neural networks to reconstruct the 3D assets. So we basically train this autoencoder first, and then we train a diffusion model to generate the intermediate, the triplane representations that we obtain from the autoencoder. And the reason it could generate augmentations is inspired by previous work on like a single image diffusion or a single image GAN. There's a couple of those work. And the main technique they use there is that when you train the diffusion models, you want a ConvNet with a very limited receptive field. So it focuses on local patterns. So when you basically train it with only one example of 3D assets, and you could generate variations like I've shown here before. So briefly mention these two work. I want to talk about the main work I want to share today, which James was mentioning, the 0123. So the question I want to ask here is like, is dataset scaling enough, right? So we look at when we compare the biggest 3D data set today, Observerse or Observerse XL, right? And the biggest 2D data set today, which is around 5 billion. So we spend like a big effort, right? We look everywhere on the internet for 3D assets, and this is the progress that we make, right? So it's pretty hard to imagine like how you would reach here anytime soon, right? So, basically I feel like it's also like just fundamentally 3D assets are much more expensive to collect than 2D images. Like with a good cell phone, you can just snap a photo, which takes pretty much no effort, right? And to create a high quality 3D assets, you either use photogrammetry to create high quality 3D scans, or you have to study software like Blender or Unity, and then you have to spend a long time editing these assets. So it's just fundamentally it's very expensive, and I don't think the right way to improve 3D generative model is to count only on data set scaling, right? Even though data set scaling is important, but we should not only count on data set scaling. And I think the way to go is to combine 3D and 2D priors. So as I said, 3D data alone is probably not enough because there's no clear timeline we could reach like a 5 billion scale 3D data sets. And we should take advantage of both 2D and 3D training data, basically. And then I feel like the model we want to have is it has a generic objective function that basically you could, with this model could leverage the priors from both 2D and 3D data, and it's easily scalable. And that introduces a 0123. So 0123 is basically a model to do novel view synthesis. And we start with a stable diffusion, which is a pre-trained text image generative models. I'm sure many of you are familiar with it today. Basically, the way it works is given a prompt like a retrospective computer, the latent diffusion model sample from a Gaussian noise and gradually denoise it to generate an image that corresponds to a text prompt. We do a small adaptation to stable diffusion. So instead of conditioning on the text prompt, we condition on an input RGB image as long as a camera transpose, right? So like RT basically is a camera transform matrix that defines the relation between your input view and your specified output view you want the model to generate, right? So 0123 basically takes an input image and the RT matrix and generate the output view for you. So this is the goal we want the model to perform, right? And the way this model is trained is basically we use Observerse and render a data set of novel views, right? So we take the 3D assets, we randomly sample 2 views, and then we basically these 2 views because everything is synthetic, we have the ground truth RT matrix here, right? So we have an input view, we have the output view, and we have the camera transform that describe the transformation between the two views. With these, we basically train 0, 1, 2, 3, and these are some of the results that we show in the teaser figure. So this is the input image, and we basically can input a few, like we ask the question, right? What does the shoe look like if I move the camera down by 30 degrees and left by 9 degrees? And that's what the model generates, right? So it's basically able to synthesize a new view of the object, which is consistent with the input object. And what's surprising is that it also works on object with very complex geometry, such as this drum set here, or deformable objects such as an elephant, right, which are traditionally very hard to model in 3D computer vision. And what's more surprising to us at the time before we submit the work was it works on paintings. So these are like impressionist paintings by Van Gogh and Picasso, and then you ask a question, right? What does the Van Gogh's sunflower look like if you put a camera on the top, and it's able to generate that view for you? And I think these results showcase sort of the zero-shot generalization ability of our model, because there's no way Optiverse as a 3D data set includes these assets, right? Because the ground truth 3D assets of these paintings don't really exist, right? And here are some more results. So from some internet image or some image I take of myself in the apartment, you could randomly sample null views, and here are the results that the model generates. And it's pretty high quality. And then it's also very consistent with the input image in terms of the identity of the object.
I mean, it is consistent at a high level, but there's lots of little details that are different, like this car at the bottom. There's decals on the windows that are in some views and not in other views. And I imagine if you put this into like an interactive viewer application, you get a lot of temporal flickering as you move back and forth.
Yes.
Yeah.
Yeah. So yeah, that's true. That's true. But I'll talk about the way. So we could basically put this model into a dream fusion type of, like, you basically extract a 3D representation from it, which is guaranteed to be 3D consistent. Right. Yeah. So yeah, I'll come back to that later. So we created a Hugging Face demo. So you could try it out. I'll put it on your own image. Maybe some of you have tried it, but yeah, basically here's the link. And a nice property of using the diffusion model here as the backbone is that it's a probabilistic model, and it models uncertainty of the problem pretty well. So not like a single view non-view synthesis is highly under constraint, right? So given an input image here, uncertainty is you don't know what's the focal length of the camera, for example. And the model is able to basically, when you sample clusters of random seeds, give you different results that correspond to the uncertainty, right? Also, you don't know what the back of the car necessarily look like. It gives you that sort of a distribution of possibilities. And yeah, so the non-view synthesis, because we use basically image-to-image translation model, and it's definitely not guaranteed to be consistent across the views. So we could put this into a score distillation framework, which is used in the Dream Fusion. So we use a alternative to that because the Dream Fusion paper is not open source. So we use score Jacobian chaining, which is follow-up work. And we basically are able to, so putting 0, 1, 2, 3 in this framework, we're basically able to extract these 3D representations like a nerve, right? So across the views, you get consistency. And following our work, there are more basically stability. The company improved upon our framework and sort of basically create they have a code base to create these image to 3D assets that's much higher quality than our original results. And you could also turn it into a watertight mesh. So it's basically, you could create an asset that's directly usable for relighting and different purposes. And there's also this recent work, I think, that's released like less than a month ago that uses Gaussian splatting instead of NERF. in this optimization framework, and they show that it's at least 10 times faster than our original reconstruction from a single image. Yeah, and here's their website. Yeah, so I feel like with this sort of by using the power of foundation models like Stable Diffusion, we sort of unlock the possibilities of doing zero-shot 3D fusion. And so ever since we released our paper in March, there's plenty of follow-up work, like 1, 2, 3, 4, 5, which does 3D reconstruction in only 45 seconds. There's Magic 1, 2, 3 that combines 3D diffusion priors with 2D, so like Dream Fusion plus 0, 1, 2, 3 type of approach. And there are 2 consistent 1, 2, 3 that address the question you asked. So apparently they also have the same question, and in iClear this year they want to address this problem, and this is like a concurrent submission. And there's High 5 1, 2, 3 that try to improve the fidelity of our framework. And there's MV Dream that wants to diffuse, basically you could diffuse multiple views at the same time from a single image, right? It also somehow improve the consistency, but also the efficiency. And there's scalable 3D captioning that use sort of 0, 1, 2, 3 to caption 3D assets. And there's Dream Gaussian that I mentioned that replaces the nerve with the Gaussian sliding to accelerate the 3D construction framework. So I think it's a super emerging field, and there are many possibilities. And I feel like there are also a lot of unsolved problems in this field. All right, now we make it work for 3D object web of scenes, right? So I feel like there are a lot of possibilities in this, and it's a very exciting field. And I feel like a lot of people are very interested in it and produce a lot of amazing results every day on Twitter. Yeah, so like I want to ask like a brief question here. So I don't have any experience with robotics, but sort of I feel like with 0, 1, 2, 3, we sort of channel the priors or power of 2D foundation models to 3D computer vision, because data is the biggest problem. So that's apparently helpful. And in robotics, data is a more serious problem, right? Like the biggest robotics data set, there's a paper called RTX that's by Google, collaborating with a bunch of institutes. They basically pull 60 different data sets across the years, and then they create the biggest robotics data set ever, and it's this little dot here, right? So I guess the interesting question, like academic questions here to ask is, can we follow the similar logic, right? Use the priors from 2D and 3D to help robotic tasks, which I think is very exciting.
I also don't know much about robotics, but when you say it's a robotics data set,
right?
What does that mean? Like, what is in the data?
Yeah, so it's basically, from my understanding, it's a bunch of recordings of robot arms, doing mostly manipulation tasks, and they record the actions between each.
Okay, so it's sort of like video trajectories annotated with like, this is what the arm was actually doing.
Exactly, yeah. So the state of the robots and embodiment of the robot, like what type of robot arm it is. Yeah, it's a great paper. But yeah, so like the apparent problem is that this has still not enough, right? I think this also it's also a problem that the robotics community are discussing. Right? They want to learn from the success of vision and NLP, but the problem here is how do you scale up the data? So I think this breeds a lot of interesting research questions. Yeah, so that was the sort of first half of the talk where I talked about how do we get better 3D generative models, and the second paragraph I want to talk about basically a few work that I use 3D generative models to solve 3D computer vision tasks, for example 3D reconstruction. So I want to start with like an image here, right? So this is like a nice image of a living room, and I can guarantee that there's no 3D reconstruction method today that could accurately reconstruct this 3D room, right? Because it's so complex, right? So 0, 1, 2, 3 maybe allow you could segment parts of the image, reconstruct every image, every object separately, and maybe there's some way you could incorporate depth to put them into their places. But still, it's a very challenging problem, right? And I also don't know the question to that, like how do we reconstruct this room, right? I don't think there's a good answer to that. It's a very hard problem. But I think there are a lot of information basically we are not using in models like 0, 1, 2, 3 today, right? And those are basically, there are a lot of visual cues in this image. For example, there's texture of the object, there's shadows, there are shadings, and there are reflections, right? So a lot of these clues could help us reconstruct this room, especially overcoming some of the physical constraints. For example, some objects are occluded behind other objects, right? This is something that generative models cannot really solve for us. Yeah, so I want to propose sort of my version of the solution to this problem. I want to like talk about this paper which totally inspired me. So it's a paper by Alan Yu in 2006. It's called Vision as Bayesian Inference Analysis by Synthesis. So he basically talked about like I extract three key points here, right? So Alan described a model which is a method which contains the generative models of images. So apparently he was trying to study 2D vision instead of 3D. And then there should be a mechanism to make proposals of objects and scene structure from visual cues. And then the way to accept the right solution is to accept the proposals with low-level cues because it's sufficiently unambiguous. So that sort of brings me to this sort of a mental framework that I want to talk about, which is to do 3D reconstruction with analysis by synthesis. So the way this work is, so we have a generative model which has some input latent space, right? The generative model architecture could be VAE, could be GAN, could be flows, it could be a diffusion model, right? And there should be an input space to the generative models. So it generates you could randomly sample some initial gases of the scene, like the room we're trying to reconstruct. And we could render this image by using differentiable rendering. So there are many techniques in differentiable rendering that are mature enough, developed by the graphics community, that we could basically readily use, right? And with differentiable rendering, we could basically differentially render a bunch of images, for example, texture, shadings, and shadows and reflections. And our job is basically, compare the difference between the rendered image and your observations, right? Because the whole process is differentiable, you could basically backpropagate your gradients, like from here all the way to your input space of your generative models, right? So you're basically trying to optimize in your input space, and then when your rendered image is close enough to the observation, you basically obtain a reconstruction of the 3D image. Right? So that's sort of overall framework that I have in mind, and I'll talk about a few examples that I practice this framework. So I want to start with reflection, as James has alluded to in their introduction. So we studied the problem of 3D reconstructions of human under complete occlusion, right? So in this image, there's a car, and there's a person that's like occluded behind the car, and assuming that's the person, right? There's no way you could basically reconstruct the 3D human, right? Like 0, 1, 2, 3 doesn't give you that level of prior to do that. Just physically impossible, right? But what would make it impossible is if the car in front of it turns into a mirror, right? And then we could basically see the reflection of the boy, and then we could use the reflection to provide non-line of sight information for us to reason the 3D pose and 3D location of the human. And it turns out that in infrared cameras or thermal cameras, cars are basically mirrors. So this is a side-by-side comparison of two videos, right? Like on the left is a normal video, and on the right is the video recorded by a thermal camera, right? They have the same view. You can see the wheels of the car are the same, but you see no reflections in the normal camera, but there's a very clear reflections of myself, right? Walking in front of the car. And why is that, right? What's the underlying mechanism that caused this? So that comes back to black body radiation. So basically, in real world, every object emit some sort of some level of radiations. Hotter objects emit stronger radiations, right? And the radiation is also a function of temperature. So like when you heat up an iron, it creates visible light. And as it cools down, you don't see the visible light anymore. But that's because the infrared radiations the metal emits has a longer and longer wavelength as the temperature decreases, right? So it turns out that because the human body is like 37 Celsius in temperature, and emits a very long wavelength infrared light of 9.5 microns, which is about 10 times longer than visible light spectrum. So you don't see people glowing in the real world, but with this type of thermal camera, right, you can basically see human bodies as a light bulb. So the message here is that human bodies are basically long wavelength infrared light bulbs. And the goal is to use these clues to reconstruct 3D human body. Yeah, so here are some examples, right? So you can see my roommate dancing here, and when you turn off the light, you don't see anything, but you still see the same image in the thermal camera. And cats are also infrared light bulbs. And as I mentioned, right, there are many surfaces are more reflective basically in the infrared. For example, glasses. This is a specific comparison as well, right? So you don't see any reflection in the normal camera, but you see a very nice reflection in the thermal camera. And like whiteboards in our lab, you don't see any reflections in the normal camera, but very clear reflections in the thermal camera. And the cars I showed before. And they're bowls here, ceramic bowls, metal bowls. They're all very nice reflectors of infrared. Right, and here's a very nice example. So in the normal camera, if you have a very polished metal, right, it could probably be a good mirror as well. But you don't see a very clear reflection on the left because the surface is more or less matte, right? It's a little bit rough. But you see a very, very clear reflection in the thermal camera. Why, right? The reason is because the wavelength of infrared is longer, so it has a higher tolerance for rough surfaces. So basically, with like a matte surface of the metal, you could still see a much clearer spectral reflection in the thermal camera than in the normal camera. So with these phenomena, so I want to talk about the method that we use to reconstruct 3D humans from reflections. So following the framework I talked about before, we have some input space, some latent variables to generate and some generative models, right? To generate the scene. So we have the object generative models here generate an object in the scene, and we have the human generative models here, which is SMPL, right? To generate the human body. And we know we also have a thermal camera here, right? So the high level idea here is we want to do differentiable rendering of reflection to render what the thermal camera can see in terms of thermal images, right? And we can compare with our observation, which is what the camera actually captured, right, in the scene. And by calculating loss, we could backpropagate all the way to the latent variables here at the beginning, right? Because the differentiable rendering process is differentiable, and the generative model is also differentiable. So by finishing this optimization cycle, the hope is that we could reconstruct the 3D human body, post the location of the human body. And yeah, so I talked about a high level idea here, but what is differentiable rendering? How does it work? So I'll give like a pretty brief introduction of differentiable rendering. So in differentiable rendering, you assume there's some scene parameters, the materials, light, cameras, and geometries. And through a rendering process, you basically could render images like meta image, RGB image, depth image, silhouette image. And you could compare with your ground truth observation with some objective function, right? And because your rendering process is differentiable, you could backpropagate that loss into your scene parameters, so adjust these scene parameters, right? So that's basically a high level goal of differentiable rendering. And here's like a 2019 work, which is a good example of differentiable rendering. So in the standard rasterizer in a graphics engine, right? The way you render an image is you basically project all the triangles of this 3D mesh towards your camera or your image plane, and then you find the closest pixel to the triangle, and you basically copy the color there, right? And this copying process is apparently not differentiable. So this paper came up with the method. So this paper is called soft rasterizer. So it's to basically make the influence of the triangles on every pixel to be soft, right? So instead of just copying values, you aggregate the influence of all of the triangles on the pixel as a function, right? And then this function is differentiable. So you could basically backpropagate your gradients into the 3D triangle meshes and to make this process differentiable. So we follow a similar method in our paper to do 3D human reconstruction under reflection. But there's still a problem that remains, right? Like you could march your triangles towards your camera, but when you have a layer of reflections, right, you can't do that anymore. So basically in graphics, when you're trying to, this process of marching the object towards the camera is called rasterization. And because we have reflection, we have to use what's called ray tracing. So we have to march the rays from the camera to the object instead. And here's I described the process. So there's a light source, which is human bodies, right? It's a triangle mesh. And there's the object, which is object D plus DF. And what's nice about D plus DF is that you could basically specify a point and you take the first degree gradients, and that give you the surface normals of the object. And you have the thermal camera sensor. So for every pixel in the thermal image, you could shoot out a ray from the thermal camera. And then that ray is well defined, right? Because you have the 3D coordinates of the thermal camera. You have your pixel defines the 3D ray. So you have basically the vector formulation of that ray. And you could ask the question like if whether it intersects with the object as D plus DF, right? So you could basically find the point of reflection that's close to the surface of the object D plus DF. And you could query for the surface normal, right, by taking the first degree gradient. And you could basically analytically calculate what's the emitting ray from that surface, right? So all of the ray here has an analytical solution of their direction. And with that, you could basically calculate what's the distance from this emitting ray to all of the triangles on the human body, right? Because you also have the coordinates of the 3D human body triangle meshes. Right, so for every pixel, you have a distance from the emitting ray to all of the triangles of human bodies. And with this information, you could basically do soft rasterization with the exact same loss function and optimization process as the 2019 CVPR paper. So yeah, so I probably have glossed over some of the details. So if you have more questions, feel free to talk to me offline. Yeah, so let's look at the results, right? So this is the input RGB image that we take. So interesting story here, like we actually didn't include the car experiments here in the original submission, but some reviewers saying that why don't you try it on cars? So we like rented 2 cars in New York City to drive it to the closest parking lot we can find in New Jersey. Yeah, in a rainy night. So yeah, it's a little bit sad. Yeah, so this is the input car you see, right? You don't see the humans, and we're trying to reconstruct the human that's standing behind the car that you don't see. And here's a thermal image, right? It contains some reflections of human, like as a form of like a silhouette. And here's our reconstruction of the scene. So we first reconstruct the car, and we use the car to reconstruct the human location and the pose of the human body. And this is sort of the ground truth scene that you should compare our reconstruction against. And so you see there's still some difference because information here is highly limited, right? And our optimization algorithm is not perfect. But it mostly get the 3D location of the human correct and pose correct, right? And here are some more examples we collected in the lab. So with a bunch of bowls here, they basically with arrays of bowls, you basically get multi-views, right, of human reflections, and we are able to reconstruct the human body pose compared with the original scene. And we also try it on like bowls. So these also work pretty well. Yeah, so just to sort of put things together a little bit, we use the generative models of which is in form of a VAE, right? Because SMPL uses underlying the V poster uses a VAE architecture, and then the differential rendering here reasons the reflections. So we optimize in the input space to basically reconstruct the human body that creates this reflection image that you see.
Are you also using some sort of key points in the thermal image to guide the simple model?
Key points as in
Some sort of like key points around the human or something.
so I'm not sure exactly what. Yeah, so I can so we basically in more detail. So the thermal image we basically pre-process with some sort of denoising, and we extract like a binary map of like a silhouette basically, right? In terms of like the SMPL, it's a 3D mesh. So we basically run differential rendering of that 3D mesh to create a differentiable binary mask, and we take the loss.
Okay, so you take the loss between mass.
Yes,
Okay.
yes. Not key points. Yeah, yeah. I see. Right. Yeah, you could render because you could render every pixel. So you can just take some sort of MSE loss between the binary reflection silhouettes and your rendered image. Yeah, but what's nice about this is that the whole process is differentiable. So like every pixels of your rendered thermal reflection can be backpropagated into your input space of the VAE to adjust the human pose and location of human. Right. And another image, another example I want to talk about here is shadows. So it's also another type of visual cues, right? So the problem we're trying to study here is by only looking at the shadows of an object, and you reconstruct the 3D shapes of that object. So to do that, basically, we need to reformulate our like previously introduced differentiable reflection rendering into a differentiable shadow rendering, right? Which is much easier actually. So with the light source, you basically for every pixel in your image, right, you shoot out a ray, and whether there's a shadow there is basically if you densely sample along the ray, that ray is blocked by the object or not, right? If a ray is blocked by the object, then there's a shadow. If the ray is not blocked by the object, it hits the ground, then there's no shadow, right? So you could basically sample density along the ray, and as the object is represented by an occupancy function, you query the occupancy function for these points, and you aggregate them basically. You find the maximum occupancy value, and if that's occupied by an object, and there's a shadow on the ground. Yeah, so we run the same optimization process as I mentioned before, except the differentiable rendering process is replaced by a differential shadow rendering instead of differential reflection rendering. So given an input shadow here, we sample some random initialization of a generative model of planes. And this is basically the shadows, right, extracted from the image on the top. And we run this optimization process, right? So we try to minimize the distance between the predicted shadow in the middle and the ground truth shadow, right? At the end of the optimization cycle, you see that the shadows are pretty well matched. And the shape also matches the original objects. Right? And here are some more examples of the like running this reconstruction algorithm. So you could reconstruct chairs. That's pretty much completely occluded behind this red chair, right? And you could, different type of chairs. You could run it on a pickup truck, right? Because you see the shadows here, you could reconstruct the truck, the car. More cars and Jeep. And it also works on real world images. So apparently, like there's a data set, and there's even a line of work that's on shadow detection or shadow instant segmentation. So basically take some of the data from the data set, we extract the shadows with their algorithm, and then we run our algorithm on it, right? And it's able to reconstruct these real world 3D objects from the predicted shadows in the data set. And there's a problem that remains here, and I guess you might have seen before, is that there's a very rough landscape, lost landscape. So because we are running a optimization algorithm, we're solving an optimization problem, and this optimization problem is highly non-convex, which creates this instability. So it makes it very unstable. It also makes it very inefficient. So it takes like 300, 200, hundreds of iterations basically for you to reconstruct one image. And in the last talk I want to share, I want to basically, we propose a method to improve this slowness of optimization. Yeah, so the problem here is that we have a forward model, which is the generative models of shapes, right? In the previous example, it generates some shapes and it has some shadows compared with the ground truth. And you run your optimization in the input space of the generative models to get your final 3D scene that recreate the shadows. And the problem here is that the landscape here, if you visualize in PCA, it's a very rough landscape. So if you run optimization here, you basically have the instability that you see before, right, in your latent trajectories. And the method we propose here is we learn a new latent space, basically, which is, so we call it learning to remap the landscape. So instead of optimization in the X space, we create a new theta, which projects from a new Z space to the X space. And we have an amortized training algorithm to train such that optimizing in the Z space is much more efficient than optimizing in the X space. And if you visualize the landscape, it becomes much smoother in terms of the lost landscape. And here's some, so the shadow was one example, and here we also show another example of doing GAN inversion, because GAN inversion is also a neural network inversion problem, right? And we show that our like if you optimize in our landscape, it's much faster than the baseline, right? And also,
Roshi, sorry to interrupt a little bit. You only have a couple of minutes left. We're running a bit out of time.
right? Oh, okay, yeah. I'll finish very quickly. Yeah, it also works on 3D human reconstruction, which is also a neural network inversion problem, right? Yeah, so to put this back into the analysis by synthesis framework, we are solving the same problem, but we try to add like a new learn input space here, right, to accelerate this process. So it's still under the same framework. It's just we want this process to be faster. Yeah, so to recap, I talked about sort of 6 papers today, and the first half of the talk is about how do we build better 3D generative models, right? We scale the data set and we combine 2D and 3D priors. And the second half of the talk, I talked about, once we have better generative models, can we put it in analysis by synthesis framework, right? Which allows you to leverage a lot of the visual cues in your image that to reason like different 3D geometries and solve problems like occlusion, for example. And at the end, I want to thank all the co-authors from Columbia and different other institutes. And it's definitely, these papers are not possible without their significant contributions. Yeah, thank you very much.